Alright, so I want to talk about power and how it relates to thermal energy, and really this is all just conservation of energy, because remember thermal energy is just a type of energy. So power is work divided by time. Remember work energy theorem, work and energy are the same thing. So power is change in energy, or how much energy you expend or is expended, divided by time. That's how much power is being exerted, energy divided by time. Well, a type of energy is thermal energy, so delta Q divided by time is going to be power. Now, we have two equations for delta Q. If we're heating up a substance inside of the same phase, solid, liquid, gas, right, and we're not changing its phase, then delta Q is mass, specific heat, change in temperature, MC delta T, because that's the point of whenever we're staying inside the same phase, you pump in heat, the temperature goes up, delta T. Or if we are changing phases, no temperature change during a phase change, going from like a solid to a liquid, then we're using latent heat, ML. So power could be thought of as thermal heat, MC delta T, or ML, divided by time. Now this is very useful whenever you think about how long would it take a water heater to do something, or how long will it take a stove, a electric stove rated at such and such watts, that's a power, right? How long time will it take a 3,500 watt stove to raise the temperature of water from 0 degrees Celsius or from 20 degrees Celsius room temperature to 100 degrees Celsius boiling. You're solving for T there. So that's the idea with power. You're able to see whenever you connect power with thermal energy, you're able to see that in terms of time that it's going to take. Another application you'll see lots of times with this idea of power, and I just use the MC delta T one, is flow rate. Like an electric water heater, like this guy down here. Water flows in cold, and here I have a chemical burner going on, but that doesn't matter. It would have a rated power as a chemical burner, or maybe this is electric down here, and it provides heat, and as the water flows through here, it gets hot and then comes out. So what flow rate of water can such and such watt heater, such and such power in terms of watts, heater support if it's meant to raise a temperature from what to what? So like if I have a 1,000 watt heater, that's your power, and I'm trying to raise the temperature of water from 0 degrees Celsius or from 20 degrees Celsius to 50 degrees Celsius, my delta T, 50 minus 20 being 30 for delta T, what flow rate? Now this flow rate is in mass per unit time, or kilograms per second. But that's fine. That's a perfectly legal flow rate, and it's really easy if you're just dealing with water to convert from kilograms per second to a volume per second, because remember 1 kilogram of water has a volume of 1 liter. So mass per second, if we were in waters, that's also liters per second volume there as well. All right, so I want to work a couple of problems showing applications. Alright, so in this problem I have a tankless water heater, and I'm trying to see what flow rate could my tankless water heater heat up. If it's rated at 750 watts and we need to heat this water from 20 degrees to 50 degrees Celsius, what flow rate do I need to have? In other words, if there's too much water coming past, the heater won't be able to keep up. It won't be able to warm the water all the way up to 50 degrees Celsius. I just noticed I'm going to come back in here and I'm going to give myself decimals at the end of that, so I apologize for that mistake in the typing. So what flow rate am I going to need? Well, power, and I'm going to work back through this, but power is energy. In this energy, we're talking about delta Q over T, right? Energy divided by time. And delta Q here, because we're staying in the same phase, water, 20 degrees Celsius, 50 degrees Celsius, it's still liquid at atmospheric pressure. So I'm dealing with MC delta T, heating up inside the same phase, as opposed to ML, latent heat, whenever we're changing phase. And remember I showed earlier, right, if we connect our mass and our time into one thing, I get power equals a flow rate, M over T. Treat that as one variable, M over T, C delta T. And now it just becomes plug chug. And whenever I work that math through, remember specific heat of water, 4,187 joules per kilogram Kelvin, delta T, final minus initial, my 50 minus my 20, I come out with about 0.006 kilograms per second, which is an incredibly small flow rate. I mean, we're talking about 6 grams per second of water. Remember, 1 gram equals 1 milliliter, so 6 milliliters of water per second. This isn't even a trickle. We're talking small drips of hot water coming out. So in other words, water heaters, if you're going to use this kind of water heater, you're going to need a very powerful one. You're going to need something in terms of thousands or 10,000s to be able to heat up the quantity of water that you need, specifically because the specific heat of water is so large, you have to apply a lot of energy. So energy per unit time, you're going to have to be able to apply a lot very, very quickly. So you're going to need a much more powerful hot water heater. Now this is a good example of using power, how it connects with thermal energy here. So, breaking delta Q into MC delta T. And then in this problem, we were talking about flow rates, so we combined mass divided by time to get a flow rate. You'll find some problems that are connecting power with thermal energy, and then they give themselves away, right? They either ask how much power does something need, or they actually give you a power, look for the units watts, look for the units of watts. Sometimes they won't require a flow rate, so you just won't combine M over T. It might be asking for how long, and you'll actually be solving for time there, or some other part of this, but if it's not giving you a flow rate, there's no reason to combine, or asking for the flow rate, no reason to combine mass divided by time. Alright, so in this problem, we're looking at a car coming down a 1.2 kilogram tall mountain, and how hot are these steel brakes going to end up becoming? And we got to make a few assumptions in this problem. First assumption we have to make is that energy is conserved and not lost to the environment, which is not true, right? A lot of the thermal energy that's going to be produced on these brakes is going to be lost to the air around. So please remember that, take that into account whenever we get to the answer. But we don't have a good way to calculate in this course how much, or the rate, if you will, how quickly an object like steel gives off thermal energy to the surrounding air. There, a rate of that. So we don't have a good way to deal with that. And then we deal with time coming down the mountain to actually see how hot it was at the bottom. But we don't have a good way to deal with that. So we're going to assume that energy is conserved, not lost to the environment around. Now, that assumption isn't a good assumption, but we can kind of get the idea of what's going while making, the idea behind this problem while making that assumption. This next assumption is a good one, that the car was going at a constant speed at the top of the mountain and would like to be going at the exact same constant speed at the bottom of the mountain. So in other words, the car's kinetic energy at the top and the bottom should be the same. So none of the kinetic energy is being converted into thermal energy. Now, if you think about brakes, brakes operate by friction, right? They use friction to steal energy from a car. So whenever two things rub together, I mean, you can take your hands, you can rub it together again if you need a reminder. Friction, the way it steals energy, is it takes energy away, energy of motion generally, right? Not generally, kinetic energy, it takes it away. So as the potential energy is getting converted to kinetic energy, the brakes are stealing all that away to hold the kinetic energy constant, and then throws that energy off into heat. You rub your hands together and they warm up. So this is a conservation of energy problem. What we can say is change in potential energy, how much potential energy you gain or lose, equals your change in thermal energy here. So MGH, specifically of the car here, right, how much potential energy the car gains equals MC delta T of the brakes, how much the brakes heat up, if you will. And we're looking for, let's see, how hot would a car's 34 kilogram brakes get? We're not given an initial temperature, so we're going to solve here for delta T. If we really want to assume and see what was a temperature, not just an increase in temperature, we'd probably assume 20 or 21 degrees Celsius, an average day outside, 70 degrees, something like that. And you can go a little bit cooler or a little bit warmer depending upon the season if you'd like. So now we're substituting in numbers and solving for delta T. Alright, so now I've substituted in all my numbers. Remember, the potential energy that we're converting into thermal energy is all the potential energy of the car itself. That's why MGH, I use the mass of the car, which is listed at 780 kilograms. Also, don't forget, you're told your height of the mountain is 1.2 kilometers, so convert that to meters over here. And the thermal energy over here comes down to the brakes. I was told the car's brakes, plural, so I'm going to make the assumption that this is all the mass of all 4 brakes combined. And that seems about right, 34 kilograms, right? If I was told 1 brake, then a mass of 1 brake, I'd have to multiply that times 4. The specific heat of steel, I'm going to use 466 joules per kilogram Kelvin. Now, steel is an alloy, meaning that it is a man-made thing, so the properties of steel can vary with specific heat slightly, not a lot, albeit otherwise it wouldn't be the same. It wouldn't be the same alloyed steel, but it's going to vary slightly because the mixtures of the metals going into it might vary very slightly, also man-made. And then I'm solving for delta T. But just remember over here where the energy is coming from. Potential energy is potential energy of the car, where the energy is going into. Thermal energy of the brakes, so don't mess up your masses. All right, and our answer is that the brakes temperature would increase by 580 degrees Celsius. Now I purposefully set this up this way with that incorrect assumption in the very beginning to demonstrate a couple of things, right? This is a massive change in temperature. So this would be like a car pretty much coming straight down the mountain, just having to ride the brakes the entire time. You're going to get a huge delta T. In other words, your brakes are guaranteed to fail long before 580 degrees Celsius. So there are 2 things that are recommended in a car to prevent such a high increase in temperature. Well, 1, we know air actually steals some of our thermal energy. The environment around steals some of our thermal energy. So we need to lengthen the time it takes to get down the mountain while you're on your brakes. That way air has a little bit longer. We're not going to convert our potential energy as fast. So what people do, what engineers do, is they don't take you straight down the mountain. They wind the road all the way down. Whenever they're winding the road all the way down, you're not converting as much potential energy into kinetic and then having to use your brakes to convert that out to friction. So you're not going to heat up your brakes as quickly. That gives air more time to cool them down. But on a steep mountain, especially one that's relatively high, winding the mountain's not going to be enough. If you're on a steep mountain, you're still going to convert it too quickly. Air's not going to be able to keep up. You're going to heat up your brakes. You're going to get a huge delta T. Your brakes are going to end up failing. So the other thing to do is don't use your brakes. The recommendation coming down a mountain is to downshift the engine. Automatic engines generally have, let's say, 1st and 3rd gears that you can downshift into, sometimes 1st, 2nd, and 3rd gears that you can downshift into. So what you do is you downshift into one of those. That lower gear ratio won't let the car go too fast. The gear starts to hit kind of top RPMs, and the engine itself starts to hold the car back, meaning you don't have to ride the brakes all the way down. Thus, you're not converting as much of your thermal energy, right, or your potential energy into thermal energy. You're not heating up the brakes as much because you're not hitting the brakes, because you're using the engine to slow yourself down as well.